I do have a question about that though.
Yes.
So what happens when an insulated material comes in contact with something that's highly charged?
All right, so very similar to sort of the first thing we did. So let's take the balloon and wall bit. Wall, balloon. Let's assume it's an insulator. I mean, for the most part, walls are not designed to conduct electricity, fortunately, since there's an electric plug and electricity in here, a lot of it. If I take a balloon and rub it against my head, balloon being closer to rubber, we'll end up with, well, we start out with a whole bunch of evenly spaced positive and negative charges. Assume there's the same number of plus and minuses there. When I rub it against my head, it's going to pick up excess electrons. Wherever, on the point where I rub my head on it. When I bring this close to the wall, what's going to happen?
The electrons are going to move away.
How far?
I guess it depends on how many electrons are on the balloon from the hair. How charged it is.
In theory, yes. Realistically, you're not going to have enough electrons on here to. Oh, let's hear what Daniel has to say before I finish my sentence.
Well, because it's an insulator, it's gonna have a hard time moving through, so it will try to, but it will have difficulty compared to if it was like a metal wall.
Yeah, and that's what sort of what I was going towards here. That it does push the electrons away if it is theoretically possible, if this has a high enough negative charge that those electrons will get ripped away from the atoms. But this is an insulator, or insulating material, it's an insulator. And so the electrons try to move away, but they're not being ripped out of the atom. But they're still attached to the atom, so what they're gonna do is they're gonna shift. Now I'll make it seem like it's an all or nothing thing. I mean, they have a tendency to move to that side of the atom. So now, I have positive charges attracting. I have negative charges repelling. On the whole, which one's closer?
On the whole?
Yeah, I got repulsion and attraction both going on. Because I got protons here and electrons here. In general, which one's closer to the balloon? Positive or negative charges?
Positive.
And that is going to be the dominant force. And so that attraction, because of how close these are to each other, so you can expect distance to show up in the formula. Because of how close they are, this attraction will be a dominant force over the repulsion. Thus, balloon sticks to wall. Thus, the straw was repelled. Sorry, the straw was attracted. Down was addressed, light repelled. My theory.
Does it have to do with the triboelectric effect?
Well, I was rubbing one thing against another. I think tribo comes from the Greek word to rub. Yes, it ultimately comes down to that, but not. I think we're thinking about it in two different ways, though.
Okay. I'll just go ahead and explain.
No, I don't mind them.
Can I ask a quick question?
Yep.
Would this happen in a more localized way, like where the balloon is near the wall?
Yeah.
That would shift? Okay.
In theory, it would happen all over the place, but at some point, you really can't tell.
Does it matter that it's an insulator? Like if it were not an insulating material, imagine it would behave different.
If this were insulating,
We're assuming it is insulating.
right, if this is a conductor here,
Yeah.
the electrons would move farther away and it would stick better. Because the repulsive force, you've got a greater distance between the electrons, and so the repulsive force is not as strong. And if the balloon were a conducting material, what would happen when you rub it against your head?
gain negative charge?
Would your hair stick to it better?
No, well, assume that your hair and the balloon are now metallic balloon are both neutral to start with. I would claim that it would pick up electrons, but where would those electrons go? If it's, because I'm holding a balloon here and I rub it against my head, if
Would
it
it
picks up
just-
electrons, where would the electrons go?
It would diffuse into you.
Yeah, it would come back into me. So I think you'd get the cycle going. That's why I hesitated when you said, I mean, the net result is, I think, no electron, same number of electrons. So,
Yeah, I understand.
all right, so when I had the neutral straw, and I rubbed, whichever one was it? I think it was this one, and it repelled. I was expecting really this type of effect here, which we noticed when I rubbed the other material. When I neutralized this, I neutralized the outside. I ran water over the outside, dried it off. My speculation is that there was a charge inside. There was some sort of positive charge inside, which I think was being speculated yesterday, or last 4 days ago. And I sort of dismissed it because that wasn't what my head was. I apologize. And so when I brought the negative charge towards it, whichever material was negatively charged, when I brought the negatively charged material towards it, it not only had the attraction for the positive charge inside, but also some of the pulverization effect. But yeah, I still like that one better resolved.
So when do you start getting charges, like where you have a large amount of positives on one side and a large amount of negatives on the other?
Reword that? Or say it
When do
again?
you start getting like those strong poles? Like we have a strong positive or strong negative ends?
When you have a conductor, when we're dealing with insulating materials right here. But if I had a neutral conductor, and so on, and I bring something over here that's make it negatively charged, because again, minus sign's easier to do. If this is strong enough, again, these electrons can now move freely. If this is a conducting sphere over here, or some sort of conductor, so now the electrons will start to gather on one side. And leaving the positives on the other side. Ooh,
Yeah.
backwards.
Yeah.
The electrons will start to move over to the left side, exposing the positive charges. Again, it's not the positive charges moving to the right, it's that they're just now being laid bare. Did that answer your question?
Yeah, so I'm trying to think, like, we think about poles of the earth and how they have the field around them. Is that what's happening in essence? We talk about the poles of the earth and whatnot.
So we're talking about, you're starting getting into magnetism. Magnetism is
Oh.
caused by moving charges. And so that is caused by, there's a bunch of positive and negative charges swirling around in the core, causing that magnetic.
That's right, I forgot about that.
We'll get to that in chapter 22, I think it is.
Is that why magnets stick so well? Because like usually magnetized objects are, like when I think magnets, it's usually like a conductor. So is that why they like stick so well? Because it's like we're talking about the balloon to the wall thing.
Yeah, and why does it stick so well? For the things that, to create a magnet, again, you need moving charge. To create a permanent magnet, you basically need to have a bunch of charges all basically good enough for now, circling the atom all in the same way. So if all the electrons are traveling around like this, then you're basically creating sort of a net magnetic field. Usually the electrons are moving around in some random pattern, and so any magnetic field created by one electron is canceled out by another one. So if you have just a couple of them moving in the same direction and all the rest cancel out, you got an incredibly weak magnet. So I would not say it would stick strong. That's the kind of thing you stick to here and it just falls.
Yeah.
So the ones that are sticking really well together have been sort of fixed in place so that everything's spinning just right. Whereas generally with charge, you know, the static charge like we're dealing with here, there's so many ways that can bleed off. I mean, I had to negatively charge the thing on the rod, I touch it to here, I've lost some electrons already. Humidity in the air, some of them are gonna go off into the air. But with a magnet, when they create it, they basically fix the spin of they fix it when the spin of the electrons are just right. I don't know if I really answered your question.
You did, but now I'm wondering like, how do they do that? But like, don't worry about answering that. But now I'm like interested, like, how do you make a magnet? I've never like thought to
You
make.
expose the right material to a magnetic field, and then, yeah, now you start,
This is.
as you get into the processing aspects of it, yeah, I'm gonna.
Yeah, don't worry about it.
All right. Questions at this point before I tell you what you're thinking? Because I can read your minds.
Through charges, that's how you read our minds.
Just read the E and fields that you're giving off. You're thinking, all this stuff is great, but where's the math?
Oh.
Yeah.
Let's do the math. We know that there's attraction and repulsion going on here, so obviously there's a force. And fortunately for you, a formula that might look somewhat familiar. So first off, the notation here, the F sub E, this is electric force. And for those who had me for the first semester did, why I don't use E for elastic, because we're using it for electric. It depends upon how much charge there is. The more charge that you have in a particular location, net charge you have in a particular location, the greater it is, and so we got to take those into account. By Newton's second law, try that one again. By Newton's third law, I know that the force being applied on one charge has to equal the force being applied to the other charge. Very poorly worded, but I'm hoping you remember enough of Newton's third law. In other words, the commutative property holds, so it doesn't matter which charge is which, the force, magnitude of the force between them is going to be the same, and so that means I'm either multiplying or adding. I'm multiplying. We talked about the distance factor. The farther something is away from the charge, the less force it feels, and so we got this r squared value on the bottom. The fact that it is squared, it seems to be found experimentally. There are people who tried to figure out, is it really squared? Maybe not. Maybe it's 2.01, 2.0001. At this point, the last thing that I saw was in 1971, they nailed it down that the difference between what that really is and the number and 2, it is within 1 times 10 to the negative 16th of the number 2. So for everything we do, 2 is good enough. Matter of fact, unless you're actually studying that, 2 is good enough for everyone else. And then, of course, we got this number up front because it depends on what unit system you're working in. K sub E, because you can't have K too many times. It goes by 2 names, Coulomb's constant, or the electrostatic constant. letter. It does indeed seem to be constant. And that's equal to, in the SI unit system, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Or sometimes on a calculator, I'll just hit 99.
I'm sorry, what did you just write in the purple?
That,
Yeah, what is the, like, 8.9 times,
this is the value of K, Coulomb's constant.
okay, thank you.
On quizzes or tests, I might give you a whole bunch of decimal places, but 9 times 10 to the 9th works.
Okay.
If you get far enough in physics, they stop dealing with coulombs and they tend to deal with stat coulombs. And the advantage of using what are called stat coulombs as the unit for charge is that the value of K is 1. So you eliminate one thing to write. Now, the basic form of this, does this seem familiar to anyone? Where have you seen something of basically that form?
Gravitational pull of two objects.
It's the one with the big G that he was talking about.
Yep. So, the force due to gravity. Let's not worry about direction. Is equal to big G, mass 1, mass 2 over r squared. When I was still in graduate school, I still had some connections with the high school system, and I managed to come across it was a preliminary criteria for graduation from a South Carolina high school. It did not make the final draft, unfortunately, because I thought it would have been funny had it done it. But one of the criteria for being able to graduate from a South Carolina high school was to be able to relate gravitational force and the electric force. I believe their intent was to notice that they're both 1 over r squared relationships. But the way they worded it, not only would you be able to graduate, you'd get a Nobel Prize in physics. And I thought they should have kept it in there just so they could say, yeah, we got some of the strictest criteria in the entire world. If you actually can connect the two more than just the fact that their formulas look somewhat the same, yeah. Maybe over the weekend, Nobel Prize. Let's actually compare the two. So if I take a proton, and I take another proton, and let's put them 2 meters apart. What is the electric force between them? I am going to ignore, let's just find the magnitude of the force. Oh, man, I got something off here. This is a vector here, but I have no indication of direction whatsoever. This is the force, this is the electric force. This 1, 2 here, this is the force on charge 1 from charge 2. So if I have some charge 1 here, some charge 2 here, so the force on 1 from 2 R2 hat. So let's do a really quick rundown of what is R2 hat.
Are we seeing for Q1 or Q2 is like 1.6 times 10 to the negative 19th power?
I'm asking about this. What does that mean?
Oh, the distance between.
Wasn't the R hat direction, think it was when you had the circle and it was the direction towards or away from the center of the circle, wasn't that the R hat direction?
That was K, wasn't that K hat?
I thought K hat was.
K hat was the third dimension, so I, J, K.
Right.
Now, R hat is, as Anna was saying, away from the center.
And like, no matter what direction.
Right.
Okay.
Yeah. Unlike I, J, and K, I hat, J hat, K hat, or for those who haven't had me, you might have used X hat, Y hat, Z hat, or nothing. Did you deal with unit vectors? You did, you did not. Others, I don't know if you remember them or not, but we dealt with unit vectors. The hat indication right here is an indication of a unit vector. It is a vector, therefore it has to have a magnitude and direction. What is the magnitude of a unit vector?
Isn't it one?
Yeah.
It is, it's 1. That's why it's called a unit vector. The magnitude of any unit vector is 1. No units. The whole purpose of a unit vector is to somehow indicate direction. So the unit vectors I use for describing 3 dimensions are I, J, and K. Now the direction of I hat, J hat, or K hat is, what is the direction?
Predetermined.
Say again?
I said it's predetermined, like it's.
Yeah, okay, we'll go with that. It's whatever I say it is or whatever you say it is. You determine I, J, and K. So, other than the fact that I hat, J hat, K hat should be perpendicular to each other. So, I hat could be that way, or I hat could be that way, J hat that way, maybe J hat that way, K hat coming out. So, the IJK unit vectors are determined by, you basically, when you're dealing with a system, you make them in a convenient direction to make the math less. R hat is a little bit specialized. R hat is known as the radial unit vector. And it